Hello, everybody, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are going to take a look at our lighting today to see. I want to go in and look at the variance a little bit and see if I think that it's working the way that we expect it to be working. That's what I'd like to do. I know we really should take a look at our bounding volume hierarchy stuff as well, because we were doing some optimization and we're actually quite a bit faster than we used to be, and there's more to be done there, I think. And so that is pretty interesting, and I would like to do it. But at the moment, we sort of have this issue where we don't really know where this variance is coming from. We get a lot of flicker, and it doesn't necessarily add up quite right to me in terms of what I'm expecting to see. And I'm thinking that we may have a little bit of bugginess that's contributing to how much flicker that we have. Some amount of flicker is probably expected, but the amount of flicker we're seeing might not be. And so that's kind of something that we need to figure out how to track down. It's definitely an important part of the process for us, is figuring out exactly where that's coming from. So one of the things that I think we need to do is sort of drill down on that a little bit. And see why it's happening, because what we've done so far is we've only really looked at strategies for reducing variance, but we haven't really ever looked to make sure we know exactly where this is coming from. So there's a couple things I would like to do, and some of them are somewhat difficult, but we'll see what we can do. So the biggest thing that I think would be useful to us is it would be nice if we can just see what happens if we want to use our current lighting system to compute a stable lighting solution. So for example, what we want to do is try to get our lighting such that if you just run it normally, give it enough time, if it accumulated enough samples, it should converge on a stable solution, right? We want to have architected our system in such a way that that would be possible, I believe. Now, maybe I'm kind of wrong about that assumption, and maybe part of the aspect of it running sort of in a real-time way where the lighting gets updated progressively over time is that you can't really get that kind of thing out of it. But assuming that that's not the case, then the situation that we have right now is that we need some way of testing that we actually do converge properly in that way. Because otherwise we have some flaw in the way that we're combining our samples, such that we wouldn't really, such that the flicker is coming partially from that incorrect way of fusing samples together, rather than from the fact that we are undersampling the problem. And so what we want to do is we want to make sure that the flicker actually comes from undersampling the problem such that more samples makes it better, and not that we actually have some kind of a flaw in the way that we're handling the integration of the samples in the first place, such that actually the flicker is coming from just bad math, right? Because then what we're doing is we're throwing away all of the hard work we did to do fast lighting path computations, and we're just getting a worse solution for no real reason, right? You want to make sure that the hard part of the problem is the part that's actually hard. You don't want to make the part of the problem that's actually easy be a part of the hard problem, right? So that's what we need to do. Okay. So there's a couple of things that we can do to look at this. And so let's sort of start to look at those now. I'm going to go ahead and load up the project. Let's see. Here we go. And what I'd like to do is inside the lighting routines, I want to just briefly remind us, because it's been a couple weeks since we did this work, but we've got a model where we consider what the emission levels are on a surface to basically be photons per second times some scale, right? So we sort of think about the values that we're moving around as almost like a transfer rate, right? Like the path through this surface is some number of photons per second. We don't actually, because that number would be so huge, we don't actually literally put in how many photons per second we think it is, but the value is something proportional to that. So if you imagine scaling down the number of photons by a huge amount, you know, 0.0000001 or something, then that is what the quantity is that we expect to see there. And so what we're doing is we're going through all of these and we do a bunch of raycasts, and essentially what we say is, all right, we're going to look at the number of photons per second leaving the surface that we're looking at, and we're going to assume that that number of photons per second will then be hitting us, right? And the way that we attenuate that is we just use the angular fall off between the two surfaces to determine how much of that transfer occurs, right? So you can see that happening right here. We're going to look at each of these. Oh, you know what? We forgot to... We never optimized this part of our code, too. I should say. This part of the code could probably be done in SIMD partially as well. So, you know, looking at this, the important thing to remember here, right, is that these numbers, when we, in fact, we called it PPS for photons per second, even though, again, it's not, just want to remind you, it's not actually a number that large. We're just proportional to it. So what we're doing here is saying, okay, we're going to accumulate the sample color by taking whatever the angular fall-off is and looking at that transfer PPS. And the way that we do that is we weight together all of the sample points on the surface that we hit. So when we hit a surface, we weight the sample points by their distance, which you can see happening here. And what we do is we take a look at how all of those points would have contributed to photons per second out, and then we just use that value to boost, you know, to basically sum up how many total photons per second we expect to get. So we're just going to take a bunch of those, and right now what we do is we take 16, so we take 64, right? We take 4 rays per, because it's SIMD, we take 4 rays per 16 tests, which is 64 total rays, and we sum up 64 of those into our accumulator. Some of those will be black, right? Some of those will not hit a surface that has anything, so it'll add up, you know, this will not add to anything. But for the most part, because there is ambient lighting coming from the skylight, you do have some of the... Almost everything will contribute at least a little bit of lighting. So most of the time you'll get at least a little bit of lighting. The minimum you can get at right now is whatever the backing moon color is. Now, the weird thing about this is this should really be fall off based as well. We should probably do an angular fall off so that the moon doesn't shine from the bottom, right? So really what we probably want to do is something like, for the moon color, you know, we probably want something like the ray direction, right, which comes through, where does that come through? It's this right here. So this sample 4dx, if we do get component subray, we probably want something like this. So the further up you're pointing in Z, the better for getting the moon color. And we probably would just say, look, if you're pointing down, you don't get any of that. So we probably should have had that. We never really went in and tuned that, but that's the case, right? So that way, yeah, like if you have like surface undersides like this, those should be black like they are, right? Whereas surfaces that can see the moon, like these, will have a faint moon color in them. And then surfaces like these that maybe can sometimes see the moon and sometimes can't. You can see there's more moon out here, but then there's shadow, so because they can't see the moon here, right? So for example, if I move this light source over here, so that the lights in here don't get that, we should be able to see sort of like more moon color out here. Well, I suppose, to be honest though, there's holes in here, so I guess they can see some moonlight through there. If I was to make that moon color a little bit brighter, so here's a much brighter moon, right? You can see that come in now. And so now you can really kind of see if the moonlight is falling on here, and then we look down here and you can kind of see how you get a much brighter ring here, and then the moon gets much dimmer. You can't really see much in there because it's very highly occluded. And then as you get out towards the ring, it's much brighter, right? Again, this is what's so cool about lighting. You know, I know it's a lot of work to get a lighting scheme to work. It's just it's much easier to just do, you know, the sort of Stardew Valley, like put a ring around the guy and it's brighter there or whatever, right? That takes like 10 seconds. But, you know, I don't know. I really like the sort of character that these things add. You can just see how cool that is that now you get moonlight. And, I mean, you just look at... It just adds a lot of character that this is lit by this, and you see the different colors coming through it. It just feels really good. And so even in this case where we haven't really scattered interpolation points intelligently over our surfaces yet, that'll add a huge bit of niceness in terms of interpolation quality and stuff like that. But even just, you know, when we look at what happened as a result of the simple cube-based stuff we're doing here, it just looks nice, you know? It just has a really nice feel to it, and I really like that, what that adds to a game, which is why I always think it's worth it. I'm going to shut the moon back down a bit to something sort of more reasonable. Maybe 0.4 seems like a pretty good plan. That seems good, right? Yeah. All right. So, and again, the reason that I wanted to put in that Z attenuation there is just because if people are shooting rays like out horizontally or down, they should not be hitting any moonlight, right? Moonlight should be coming from the sky. And so that was just a quick little term to add in there so that if you're not aiming up towards where the sky generally would be, you're not going to get, you know, any of that moon contribution, right? And we can get rid of these now because we're not really going to use these probably. But we can make this more complicated. That's what we were doing those for. You can make it so that as you know, depending on where you shoot, you get a gradient fall off. Something like if for sunsets or things like that, where you want, you know, brighter band sort of in one direction and then falling off to darker bands later. You can obviously do all that kind of stuff. All right, so anyway, point being, this is the part of the code here that's a little bit interesting and that we need to focus a little bit more on. So, you know, if we take a look at what's happening here with the light transfer, this is transferring the light and the way that we look at it is we don't take light away from surfaces because we just think of the paths as being stable paths. And I know this is a little bit weird, but we worked this out and I was pretty happy with it, and it did work very well compared to our previous stuff. So just to kind of go back, well, you don't have Milton open yet. Milton, there you are. So what we're basically talking about here is if you imagine some lighting path. So we want to know what the lighting is here. And the emitter that we're talking about is like actually over here. Let's say it is the moonlight or something like that, right? So what happens is it bounces off this surface, and eventually hits this surface, right? So it goes like from A to B to C. And we want to know what's going on at C. Then there's a couple of different ways we were looking at this before. One is we were looking at like storing lighting amounts here. So it was like we were keeping photons here. And then we would transfer the photons here. So we would subtract away from one and go to another and so on. And those schemes were just not very stable. We could not make that work very well. And what we worked out was that really photons per second was much more interesting, because basically what that was saying is, okay, an emitter just has a stable photons per second. It's a constant, you know, like 1.0 is the number of scaled photons per second, right, of a very bright light in our system or something, and 0.0 is something that has no photons per second coming out of it, and in between there is all of your lighting brightnesses. Then what happens is, when you do all your samples from a surface, you average all of the photons per second of light incoming that you see, and that becomes your photons per second, which then other people can see. And these averages are just meant to stabilize over time, right? So meaning as we take more and more samples for B, we just get better and better and better, right? And in theory, this would be accurate on a given frame if we just sampled, you know, millions and millions of rays coming out of a surface. We would in theory have a perfect estimate for what the incoming photons per second were for everything out in the environment. And that would just work, and it would be great. But we have a nasty situation where we have to update our opinion of what is actually happening with these surfaces, right? We have to sort of step through time, if you will. And we need to show a result periodically and continually update that result as we go. Because we just don't have, you know, an hour to sit here sampling and then come up with a particular result for a single frame, right? We have to show things in like a 60th of a second. Or worst case, a 30th of a second. That's the slowest frame rate a game can run at, right? Is a 30th of a second. Anything below that and it becomes unplayable. So what we want to do is we want to figure out how to correctly stabilize this over time such that it converges as much as possible. If the entire scene stayed still, it converges as much as possible to what the correct answer should be for photons per second for everybody, right? Now the problem that we have is that as we take these samples, right, as we do these sampling, if you assume that we took them all and averaged them all together, we would have something like, right, the summation of the normal for ray I, right? These are, let's say we're going to go from I equals 0 to infinity, right? We're just going to sample, and we'll just do this 1D here. We're just going to sample all of these. But the normal for direction number I, right? We're going to do all of these times the particles per second, the photons per second that we see in that direction. So if this is the direction, we want to take, I'm writing this poorly. There we go. So we'll call whatever the way we're looking is R, and we'll call the surface normal N, right? And we're basically trying to take a simple lighting fall-off term, so the dot product of the direction that we're going for a sample I, we're going to transpose that with N, which is the normal, right? And then we're going to look at the photons per second that we actually have here. So whatever the sample is at I, whatever we hit, right? We're basically looking to compute this sum. We want an infinite number of rays cast, and we want to sum up 1 over infinity, so we're taking the average basically, right, of all of these. Now, will we ever do infinity? No, but let's say in an offline renderer we were going to take, 4,096 samples, right? So some really high, huge number, right? So we wanted to take 4,096 samples, and then we were going to do this equation, and we were going to sum them all together, and we're taking the average, so we're just averaging them all together, right? So we just end up at the end with an opinion, a very good opinion of the complete coverage of what was all the incoming lighting, right? Now, unfortunately, what we're actually going to do, right, is this number is way tinier, right? This number is actually 64 right now. So what we're actually doing is we're actually computing the summation as I, and really it's I goes from 0 to 63, right? Or I guess we could say as I goes from 1 to 64, right? We're actually computing this. Right? We're actually computing this. Now this is what we're saying not enough. 64 arrays is not enough to actually get a completely stable lighting result. So maybe because we're doing it wrong. So is 64 enough? Question one we have to answer is, are we sampling poorly, right? And the answer is we might be. So improve the 64, one thing we can still work on. But the other thing that we have to think about is this is being stabilized by what's essentially a temporal anti-aliasing filter, quote unquote, right? Which is that instead of using this result, because we could just use this result, instead of using this result, we actually blend this result over time. So we're actually taking this and multiplying it by some coefficient, right? Some coefficient. And we're adding it to whatever the previous frame was, right? So we're taking whatever the previous frame was. If this is frame 0, we're taking the previous frame and adding it together, right? So we've really got a recurrence here, which we're saying, like, look, the F for our current frame, so I don't know what we want to call our current frame index. I guess we'll call it F. So for our current frame index, right, whatever that is, we are going to take the previous frame. Oh. How should I put this? We are going to take, I guess we could say, the lighting for the previous frame and add it to the lighting on the frame before us, right? That's just what we're doing. So this right here produces a weird effect on this equation, right? Because the true way to compute this equation, if you only were going to do it in chunks of 64, right? Well, and this for Martin's, I'm going to use, or was it, you know what? It might have been Neil. I don't remember who was chastising me for using the wrong calculator. That might have been Nixie, actually. Anyway, whoever it was chastising me for them. If you look at how many times we should have to do it, it's over 64 frames it would take us to get there, right? So what we really want to do is we would really want to compute this quantity, right, 64 times. So we would want to do the summation. We'll use some other value, t equals 1 to 64, right? We would want to do 1 over that 64, and then do the summation as I goes from 1 to 64 of each of the lighting samples, right? Make sense? So this is actually what we would want to do to compute it in 64 chunk batches. So the overall weight of all the samples would be 1 over 4096, right? This term here times this term here will produce that 1 over 4096, and we will average them all together. But that's not what we're actually doing. Instead, what we're actually doing is we're doing this every frame and knocking down by whatever our blend coefficient is, our older frames. So instead of it looking like this, right, where we have frame 0, 1, 2, and then frame 64, right? Instead of contributing the lighting 1/64th, 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 what's actually happening is each of these frames gets a totally different amount of weighting than that. This frame, and I don't remember what our blend coefficient is. It is... It is not... I don't know where it is. So did we remove this or something? No, okay, there it is. I'm like, what's going on? Just looking in the wrong place. It's fine. So here we go. This is where we do our lerping and stuff like that, right? So if you take a look at what's going on here, we've got a coefficient. It's this coefficient right here. So it's 0.05, right? So if we take a look at what that implies, if we have 1 divided by point, oops, so there we go, 0.05, there we go. You can look at what we're looking at here. So it's 20, right? It's 1/20th. So what we're getting here is we're actually seeing the first frame will start off, it will be on that frame, you will see 1/64th. There's the contribution of this frame. But then when we go to frame 1, this will get multiplied by 0.95, right? And this frame will get multiplied by 0.5. That's what's actually going to happen, right? So whatever was on the last frame, it gets multiplied by 0.95. Oops, sorry, 0.05, right? And whatever the contribution was on this frame, it gets multiplied by 0.05. Then on the next frame, this one will get multiplied by 0.05, right? This one will get multiplied by 0.95, and so will this one. See what I'm saying? Next one, same thing, right? So by the time we get to our 64th sample, we've actually multiplied by 0.95 to the 63 power. This sample right here, right? And the same was true of all these guys. They were 0.05 times 0.95 to the 63rd power, right? Well, in this case, 62nd power, right? So if you look at how much leverage we're getting, whoa, all right, don't know what's going on there. Okay. Oops. There we go. So if we look at what's happening there, we wanted each sample to contribute that much. What we actually generally get is something more like this. Right? I'm sorry. What we wanted was this. And what we got was more like that. Right? So, why is that the case? Well, the reason that that's the case is because we are biasing ourselves towards using newer samples rather than older samples, right? And the reason for that is because the lights are moving, right? It's a game and it's active. So we're more heavily taking these here, like this one right here will be 0.05. And this one back here, like I was saying before, will be 0.95 to the 63. So we will be looking at the current frame's contribution roughly, I guess 20% higher, looks like. We'll have about 20% higher contribution than the last frame. right? But in general, it seems, that doesn't seem horrible, right? As a moving average, that seems relatively, relatively sane. I don't know. So unless I'm doing that analysis wrong, it seems like that's a sane way to keep the moving average, because like the difference between those two is not awful. It's not what we would want in a stable solution, right? But it is not completely wrong. So that's okay. Similarly, what we could do to take a look at the difference, right, is we could actually do exactly what we're talking about explicitly. So the way that we would do that is we would just take and actually sum up all the samples over time and divide by the total number that we had sampled, right? And eventually we'd start overflowing. It would be nasty, but we could actually do that to a certain extent, right? And I'm not, like I said, not sure exactly how we would want to do that, but like, for example, since we're storing, I believe, this lighting point state here, what do we pull out here? So if you take a look at this, where is our unpack? So here is the So here's a question for you. Looking at this, I'll be honest, I had thought we had finished making it so that we recover the light PPS and start with that. So I guess, but we do, right? It's this value here, right? Yeah. Yeah. I was going to say, I thought I was going crazy there for a second. I was like, wait, do we not recover the PPS from the previous frame? But we do. So here's where we recover the photons per second for the previous frame, right? We just, for some reason, it's called emit, but we probably should call it something else, right? It's this value here. Yeah. So I'm going to call this last PPS so we actually know what it is, and last direction. That just makes it clear what's going on, so we don't have to like go, wait, what? All right. So what I was saying before is if we wanted to, right, where we stored this, we could just accumulate these directly, never actually do any blending, and then have an actual sample count here, right? So we could just have a sample count, and we would just divide the sample count, right? We would just say, all right, however many samples we've taken, we just divide by that number, and we get the actual, total amount that we expect. So, in order to do something like that, I think all we would have to do it would be a little squirrely because, but you know, when we load this out here, right, all we would be doing there, I don't know if we took last direction out. I'm going to take the direction, the lighting direction out for a second. So this is non-directional, right? Which looks roughly the same as directional. Makes us wonder if we should bother tracking it at all. So what I was going to say is if we want to look at what happens if we just sum these over a large number of samples, what we can do is say, all right, let's actually just store that information as well. So here's the sample count. And then we just divide by the sample count, whatever that happens to be. So yeah, like if you come in here to pull it out, we would just have something like this. So that would let us accumulate that sample count over time and just pull out whatever the actual average value was. And then when we go to put the information back, rather than doing last PPS here as something that was overwritten every frame by a lerp, instead what we would do is say, nah, don't do that. And I guess since we're not using direction, that doesn't matter. Instead, what you should do is say, accumulate this directly. Both of these. And then the accumulated PPS that we're actually going to write out, which is this, you know, what's actually going out to the textures, the lighting textures, that's going to be the divide. And I think that would give us basically an accumulator at that point. So now, like, the lighting can't animate, really. I mean, it will, because if you move the lights, it will adjust, but it won't be even remotely correct. But if you leave everything in stasis, in theory, we can make it accumulate over time. Now, the fact that I'm not seeing it do that means I must have messed something up there. Ooh, what did happen there? This should accumulate. That should increase the sample count. The output, oh, the output needs to be that, although that shouldn't have been. Oh, well, that would be it, because that sample count will keep going up, yeah. So that is what it looks like if we just let the lighting solution converge to whatever it's going to converge to. So after like a very large number of samples, this is what it would look like, right? So I feel like this is kind of a useful tool too. It would be nice to keep something like this in place because it sort of lets us know what the... It sort of lets us know what our lighting solution converges to best case, right? It'll never look better than this, no matter how good we do, right? This is the end solution, as if this was what's the word I'm looking for? It's as if this was an offline renderer. This is what we would see, right? So, yeah. I think there's probably a pretty easy way we can actually make that happen too. So here's what we could do without actually changing. I think I want to put this in as a real thing we can look at. So without actually changing anything here, we probably can keep a mode like this around pretty much indefinitely. So let's suppose we introduce a concept that's just called like light test accumulation count. And we'll just say that we'll take 4,096 frames or something like that. How long would that take? Maybe that's too many. It's probably too many. Yeah, it's way too many. So let's say 256. So let's say we're going to take 256 frames of accumulation for our light test accumulation count. Right? That's what we're going to do. Then what we could say is, all right, if we're doing light test accumulation, we'll do things slightly differently, but only slightly. What we'll say is the accumulated PPS is just going to be 1 over this, right? So we've got accumulation coefficient is going to be 1 over the light test accumulation count. Okay? So it's just a fixed, we're not going to remember how many samples we took. We're just going to assume that the number of samples is 256. Just period. That's what's going to happen, right? So we're going to do accumulation C times the box storage, right? So that's what we're going to do there. Seems plausible to me. And then what we're going to say is get rid of this, and the accumulation does happen right here, right? This accumulation happens. So if we wanted to do it that way, then we can actually say have a switch that we turn on, and if we turn on the switch, we do our accumulation, right? And then we multiply at the end by however, whatever the difference in accumulation count is, right? And similarly, we can make this a little bit more accurate here by just saying like, could really just do it this way, where we say like, hey, let's take the accumulation count that's recorded on the lighting test, and we'll just use that, right? And that seems good. So that's a constant that can just be computed, right? So this accumulation C here, and I guess it updates, right? So the accumulation C starts out here, and then it updates. So after we do the compute light propagation, right, solution accumulation count updates, right? So the accumulation C out here replaces the in sample count part here, And this has to be checked as well. So this goes away. And this right here where we have to normalize this, the accumulation C could just go right there. So what we can do is we could do it this way. We can say, look, the accumulation count start off at 0, or sorry, start off at 1, because that's what we would normally do. If we're accumulating, set to 0 unless we can do our inversion. If we can't, then we can't here, right? And then down here, same thing. And so then inside the lighting, we can actually just turn this on and off. So we can have our we can have our accumulation count here. Another thing we can do is, for this, what we could do is say, well, eventually we might just want to stop doing the accumulating at all. So what we could do too is we can make it so that we just don't do this pass anymore eventually. So we can say, look, we just won't update anything after a certain time. So if we detect that we are done with accumulation, we just stop, right? We just stop processing. So the way to do that is just say, look, if solution accumulation count equals the test, the stopping point, then just bail, right? Don't bother doing anything at all. So we can do something like that, right? And then, in theory, if we haven't messed anything up, so if we haven't messed anything up there, then we should be able to do that as something that turns on and off. So we can go here, this is running regular, and then if we just add a key for that, we can turn it on. So inside world mode, where we were doing our F key stuff before, so inside here, we've got various things. Maybe make the F3 key do it. So if we're accumulating, I guess technically we want to do that. Something like this. So I think this would let us do it, right? I think this would let us go, all right, moving around, run the real-time lighting, hit F3, stabilize the lighting, see what the solution is if we just let it run. Oh, we still got to map them back. So once it ends, we can't just do this because they change their order every frame potentially. So that's not quite gonna work. So what we actually have to do here is just assume that we have to assume that we want to keep one, full ones coming in, assuming, yeah. So we want to still do the mapping out, and then when we put the mapping back in here, we just want to say don't accumulate anymore if you're done. Now this would be one off, so we actually need to do one more of these though, if that makes sense. So what we actually want to do here is we want something like we want something like this, so that if we were going to accumulate, we set it here. So I think that would work, if I'm not mistaken. And this converges to a particular lighting solution. Looks like we're still getting some fade there, so I think we got it a little bit wrong. But we should be able to go back to regular lighting, right? Unfortunately, we have to have a way to clear... Well, I guess we don't have to. We can just let it converge like it did. But then if we move to a certain place, we can hit F3 again, and then it will restabilize the lighting. The lighting is super high at that point, so it takes a while to return back to normal, but anyway. So, yeah, looking at what's happening there. So, should accumulate, the accumulation count needs to not get incremented, so I think that's just that. So I think that should give us what we wanted to know, right? Now we can look at what a particular lighting solution would be in any given area, given a very large number of samples, and we can see what it looks like. And then we can return to normal lighting anytime we want. We probably should have a way to clear it, but at the moment we don't. So it starts off at the super bright averaged levels that have been accumulated, over time there. So that lets us know what the scene should end up looking like if everything converged. Now, that does tell me what I wanted to know, which is, does it converge to a reasonable solution? And it... Well, that's... So not really. Like, you can see we're getting slowly brighter. How is that happening? That shouldn't be possible, should it? How did that happen? If we are accumulating, then if the accumulation count is less than or equal to the test accumulation, we do this. shouldn't it just be less than? Because it's equal, it should not accumulate. Right? Because it hasn't been incremented yet at that point. Yeah, I think that's what we actually wanted. Let's try it one more time. Looks good. Okay, now I'm going to move over just to where we were having the sort of slow infinite gain before as well. All right. What's the, hold on a second, Insabot? Okay. Got 50 minutes till Q&A, it says. So that's pretty good. And I think, like I said, we want that in there so we know how our lighting solution is doing. So now we have a bit of a puzzle, I think. Because I think part of what we're seeing here is sort of the degree to which light bounces back and forth between surfaces creates sort of waves as we go. You can almost sort of see it. So when I hit the F3 key, right, you can see how the surfaces kind of oscillate down and then settle out, right? They're kind of like almost like damp springs in that regard. And I do wonder a little bit about how we want to try and address that. So yeah, this is a bit of a puzzler. So I guess what I would say is I don't really see, like, I mean, I wish I could say that I see anything really obvious in the way of, like, you know, erroneous behavior here, but I don't really. I do want to increase the sampling level a little bit. Um, I just want to see what happens if we really let these things settle out over a very high number of samples. That's like a very high number, right? So yeah, just like looking through how this is going, I feel like I want to go back to the hemisphere sampling a little bit and just see, because I feel like I don't know that there's that much we're going to be able to do to improve the sampling. It feels like relatively good with that convergence, just looking at it. It feels pretty reasonable. And so I almost feel like what we want to focus more on is the hemisphere sampling itself. And, weighting those samples appropriately and picking them maybe with a better random number generator that gives us a better coverage of the hemisphere, generally speaking. I don't know. It feels like we're going to have more luck there than looking at anything else here. Because if you look at that, I mean, I feel like that's... Yeah, I feel like that's just not gonna... I don't feel like there's much we're going to be doing with sampling over time that's going to fix that. So let's take a look. The time may have come, oddly enough, to replace our random number generator for reals with something like XOR shift. So, let me just step back a second, and let's take a look at our debug line stuff. So remember, we've got this debug line situation here, right? And inside Handmade Lighting, we have the ability to put these debug lines into practice, right? So we can do push debug line anytime we want. So what I propose we do here is I propose we create a random series, like so. And let's see here. We've got a part right here. We can do it. So I propose we make some random series, and then we just actually do a bunch of hemisphere samples here and draw them, so that we just see how our distribution across the hemisphere is for certain numbers of samples. So let's say we're going to draw, well, let's take 64 samples because that's how many we actually care about in this particular case. And let's just draw that many, right? So I'm going to take, start point. And I don't know exactly where that should be, but let's say something like that. And then I just want to make start point and start point plus, I don't know, times normal. And I want to make a normal. And so we can do something like this. And just draw some debug lines. So let's see if we actually get those. Why am I not seeing our debug lines? That's not where I want to be. There we go. So that should give us although I don't know if I guess it's because updating debug lines is not set to true, probably, huh? I guess we could do this. We probably just don't draw them if they're not updating. That ought to do it. Okay. So I believe that should give us a good picture of what it looks like. There we go. So this is what our sampling looks like at the moment, right? And it's not great, right? Like, it's very bunchy. You know, it's not very evenly distributed, certainly. So I do think we want to try to even that out a little bit more. And I'm not sure exactly how we want to do that, but again, we looked at a little bit of stratified sampling before, and I think now we kind of want to actually take this really seriously and get this down to a very coherent way of sampling this thing. So the first thing I want to do is I want to take care of the random number stuff here, because right now, again, we just never really put in a real random number generator. And so all we did was just use a random number table, which is fine, right? Like, that's what we just stuck in there, because we know this is really random, but the problem is the period's very short, right? So that shouldn't actually be part of our problem at the moment, because we're not, you know, we're not actually wrapping this. So in theory, it wouldn't make a difference. But while we're looking at this, while we're actually looking at this itself, I think now would be a good time to put in a random number generator that we can use, because we want to verify that it doesn't produce any more clumping than this, right? Because this is our starting entropy from actually cut and pasted, supposedly random data. All right. So the problem with random number generators is that you kind of have to be an expert on randomization and number theory to really know what to do with them. I am not. So I cannot really explain these particularly well to you, other than to say that the way that they typically work is they try to take the bits of a seed value, and they try to mix those bits up in a way such that even though obviously it is 100% predictable, I mean, this is the function that tells you what every next number in the sequence is, they try to figure out how to make those values pass various statistical tests, right? So they try to say, all right, if we were to look at what numbers this produces, and we look at things like distributions of those numbers, do they look like the same distribution checks that we would get on numbers that actually were random? So if we had a source of something we believe is actual entropy, which they do try to find, you know, don't know if this is going to really tell us much about them. So I'm not sure where to look for a really good example. So here you go. Random.org claims that they get randomness by taking atmospheric noise. So, don't know if that's really random, but they think it is, right? So, if we assume that something like atmospheric noise is truly random, and we look at the distribution of numbers that we get there, what we're trying to do with these, which are effectively pseudo-random number generators, such as this one here, is to produce sequences of numbers that look roughly similar to real random numbers, even though they are themselves obviously not random, because we literally have a function that can tell you what the next one is. One of the very bare minimums of properties that a random number should have is that you don't know what the next one is, otherwise it can't be very random now, can it? And so that's kind of the way to think about this. Just to go, all right, what we're trying to do is sort of look, we're trying to be a wolf in sheep's clothing here. The sheep is the real randomness, the wolf is the pseudo-random number, and we're trying to kind of pass ourselves off as a sheep, right? And so XOR shift is usually the one that I go to. The reason because it's a pretty simple random number generator. But it's the one that I usually go to only because Melissa O'Neill, not this Melissa O'Neill. Let's try that again. We don't want the Canadian singer. Okay, 2 L's. There we go. This Melissa O'Neill, who did a very good random number generator, which is the PCG random number generators. The PCG random number generators, which is a thing she came up with, she actually recommends using XOR shift in the paper on that as the basis for the PCGs, which she does. Now, if we open the paper up, and I've pointed this out on Handmade Array, I believe. Let's see here. This is a very good paper, by the way. I highly recommend reading this paper, and it's very easy to read. It is a long paper, which takes the time to explain everything. It's not one of those like short, concise ones that just like goes and blah and like leaves like 50 million things kind of as exercises to the reader. So I believe that if you go through and look here, she starts with XOR shift. And she basically says, look, XOR shift, isn't that great at producing random number generators, producing random numbers, but it's fast. And then it turns out if we do some simple modifications to XOR shift, we can actually get a really, really good result out of it, right? And so she talks about doing these permutations to XOR shift, which then produce very, very good random numbers, much better random numbers than random number generators that are actually way more complicated, right? So what I tend to do, and, I can't say that I have the credentials to really say that this is a particularly good idea, but what I tend to do is start with XOR shift and then add the additional PCG step on top of it in cases where it actually matters, right? And so that's my approach typically. So again, I would highly recommend reading this paper because basically what she talks about is the fact that a lot of these random number generators, and you could see it that's probably a faster way than remembering how to spell O'Neill. You can see here where she kind of does the comparison. You can see XOR shift down here. There's just a few things that it doesn't do, right? And of those things, not that many are really that important to us. You know what I mean? So XOR shift is pretty good if you do like the 64-bit bit and 32-bit. If you only do the 32-bit issues ones, then you've got some problems. We can do either one depending on how we want to do it. But this may be plenty good for us. If not, we can go to this. But the PCGs basically give you everything, right, that you probably want. So it's kind of nice to go, all right, the PCG is just a small step away from one of these. If we just kind of use one of these to start with, and if we see problems, we step up to a PCG, that seems pretty reasonable to me. I don't know that I've ever looked at how to SIMD one of these PCGs, though, which does make things kind of tough. The reason that I mention that is because if you look at what happens in an XOR shift, so in an XOR shift, these are predictable, right? And that's really crucial. We can implement this in SIMD and it's not a problem. A PCG doesn't have that benefit. So a PCG, if you look at, they have this pattern to them, shift by a variable amount, right? Shifts by variable amounts are really hard in SIMD. The problem is that they didn't introduce a variable length shift until really late in the game. So if you take a look at even, I think, if we allowed ourselves to use basically everything, maybe even up through AVX, actually, let me just do it this way. If you look at the shifts that you're actually able to do on, let's take MMX out of there. If you look at the shifts that you're actually able to do, if I remember correctly, so most of these are all immediates, right? So all of these are ones you just have to actually specify. These, right, you can load the count out of here, but it's only gonna shift it's gonna shift everything in here by the same one, right? So you don't get lane-based shifting. What you wanted is you wanted to shift by bi plus 15i, right? You wanted to shift by the lane, so each lane shifts by each lane. And that's just not on the table, unfortunately. Now, at some point, and I don't know what that point is, you can do it. And I don't know where that is. Let's try to find it here. Let's see. So here it is. So by the time you get up to AVX 512, it actually does lane shifting, right? And you can see that right in here. So you see how you've got the A value that you're shifting and the B value, they're both lane picked. They're both picked by a value proportional to the lane constant, rather than in the other cases where they were those immediates, like here, where you're just getting the shift is always the same. It's not proportional. So that's the problem. If it weren't for the fact that PCGs required that, you'd just always probably use them because they're just better and they're not expensive. And in Scalar, they're just fine. So like when we do world gen, we probably should just use PCG everywhere because there's probably no reason to use SIMD there and we'll be fine. And we'll get better randomness. But for something like the Raycaster, we probably can't afford to do that, is my guess. So that's just something to be aware of, right? That's just something that's a problem that PCGs have with a mismatched instruction set. When we finally someday in the distant future, if Intel ever actually can make it happen, they've been struggling to do so, unfortunately. If we can ever get an installed base of AVX 512 machines, then party time, right? Because if you look at the cost of these instructions too, I don't think they're super expensive. Unfortunately, they don't have timings on here, it looks like. But, you know, it's not I don't think these are super tank your frame rate kind of expenses either. Don't quote me on that. But so one of the nice things about this is if we ever actually got to this point, then we would have the ability to do a PCG 16 wide at a time. Bam, there's 16 random numbers ready to use, really high quality. Thank you to Professor O'Neill for that, right? Unfortunately, we can't quite get there until Intel gets us this in a wider installed base. Right now, hardly anything has this. So we ain't shipping a game with that anytime soon. So again, that's why my typical approach is just get away with XOR shift if you can. If you can't, then we fall back to the harder core stuff. And when we do world gen, I think it would probably be in our best interest to use the really good high quality random number generators, because at that point we can make sure that we do everything in scalar, since it won't matter. So anyway, if we take a look at what we actually would need to do to replace this with XOR shift here, right? You can see where we do the index seeding here and stuff like that. It doesn't really matter what we do there for the most part. But when we take next uint, what we want to do is say, all right, this is not how we're going to do it anymore. Instead, how we're going to do it is we're going to follow the guidelines laid out by XOR shift 32 here, which is to say we just start with a result value that is whatever the state is. So remember, our series, our random number series here stores this index value, which is the state. So we're just going to pull that out. We're then going to apply a series of XOR patterns to it. So we just XOR this with itself shifted up by 13, shifted down by 17, and then shifted up by 5. And then we've got our state rewrite, so we just store that back. We return that as the result, and we continue forward, right? So all of these just happen to call that, so we don't have to update anything else in here. We pretty much should be done at that point. That's should be it, right? And off we go. Now, if we want to, we can make this random series be wide all the time, so it's trivial to get one from it. First, let's go ahead. Oops, I want to do that. Let's go ahead and verify that that works reasonably well. And so now if we run this, we should see that pattern of raise. Hopefully we get something. Okay, so okay, that is not what I would have expected to see. What is our... What is our random bilateral code doing? Max random number. Oh. And min random number. All right. So our max random number now should just be all Fs, I think. Unless I'm wrong about that. So, yeah, so this is not really right. So what we want to do here is say, this should be U32 max now, I believe. Yeah, much better. So oddly enough, if you look at this, it's actually, it's really no worse, I don't think. It's a little clumpy still, but it's about as clumpy as the old one was. I don't see a lot of difference between those two. I want to raise it up a little bit so we can see the entire ball better there. So if I just, let me pop back to this and just try to push that up slightly. Of course, that'll probably land us... oops, that's not the value I'm talking about. There we go. So yeah, if we take a look at that, it's, you know, it's really not any worse than the old one was visually. And one of the reasons I wanted to wait to do this until we had something we could look at like this was for specifically this reason. I wanted to verify that we weren't going to have something that was too clumpy, and so until we actually had something that was, you know, reasonable, I didn't want to get into that. I didn't want to replace the random number the random table with something until I actually could see it, right? Because seeing it helps a lot. So let's see if there's any holes in it by increasing this number. And again, right, it looks pretty good. Like there isn't, we're not seeing an area, like if we saw a particular area that just wasn't getting filled at all, then that would be a really big cause for concern, right? And we're not seeing that, so it seems pretty good, right? So I think that's okay, and I'm okay with that, right? So we can excise this from here and leave ourselves with that. And I think that's fine. Yeah. All right. So now I guess what I'd say is, yeah, let's take a look at playing with this function a little bit and just see how we can get these points distributed. So the first thing I'm going to do is for picking the normal, I'm going to try picking a unilateral for z, so we're only picking up values. Because we know our normal is pointing straight up in this case, so we can just kind of bias that way and go. So here's our sampling, right? And what we'd like to do here is, I think we'd like to make it so that we're kind of more biased towards up, because straight out to the sides are things that don't contribute very much to our lighting, because we're using angular fall off. So I think we want to bias our sampling towards things that can actually contribute to our to us more directly. And one thing we could consider doing is not actually weighting by the angular fall off, and instead of taking a uniform sampling and multiplying the results by the angular fall off, we can just sample proportional to the angular fall off and not multiply the results by the angular fall off. Does that make sense? Meaning, what we can do here is say, look, previously what we were doing is saying, let's uniformly cast rays all through the thing, right? So we've got a uniform sampling of the hemisphere. And then we'll multiply that by the cosine of the angle, right, between the normal, because we know that's how light works, that the light can't, we don't get as much light from things that are angular because of the you know, that sort of beam diagram I drew before, right? So this cosine here, there's two ways we can get that term. One way is by multiplying it after the fact, so that we do a uniform average, right? And then we multiply by the cosine term after the fact. You know, so each of these gets multiplied after the fact. The other way we could do it is to just more highly concentrate our things so that they're proportional to the cosine in the first place. Then we just don't bother multiplying by that term. Right? Because then we're basically saying, look, we're going to take less samples in that direction, so they'll naturally be weighted by the cosine because we just are already weighting by the cosine to begin with. Hopefully that makes some sense, right? So one way we could do that is by doing sort of the I guess doing a sort of inverse square root mapping. So one way we could do that is say, all right, let's just take two random bilaterals and then set the third value just equal to whatever they would have to be, right? So something like that. And I believe that should, oh, that's not going to do it. So we just want to say, all right, the normal x and normal y, right? We just want to recover z from that, like so. And so now we get one that, yeah, is... Well, we don't really get much pointing directly up there. And also, these kind of have to be placed in the circle. So this is not quite... This creates a little bit too... This won't produce something in a disk, right? Because this is producing something in a square, and we would need it to be in an actual disks, if that makes sense. So, you know, these aren't quite right. Not sure how to do that quickly, though. I mean, one way is to just throw it out if it doesn't fit, but that's kind of nasty. We want something that can produce fairly consistently stuff that's going to be in there. So... I mean, I guess one way to do it is to pick a length. So what we could do is say, all right, you know, and this is, we can make this faster. So one way to do that there, right, is to, yeah, to pick a length. And, you know, that weirdly, that gives me only things that appear to be out in the cone, which I'm not sure. I must have that wrong here. Yeah, I've got that wrong. Serves me right for not solving the equation. So we want x squared plus y squared plus z squared square rooted to equal 1. Squaring both sides gets us x squared plus y squared plus z squared equals square root of 1. I'm sorry, square of 1, which is 1. And so it's z squared equals 1 squared minus x squared minus y squared. And as you'll notice, that has an extra term in it. That's why I always write the equation. So that needs to have that extra term in it, right? So trying again. Although that's interesting. So that was a kind of interesting happenstance. I didn't know you could produce a conic sampling in that way. So here is one that should be more biased towards the up angles, and you can see that it kind of is, right? And if I let this series kind of run as well, we could maybe get a better idea of it. Let's also let's try running it for more iterations. Maybe can we make it a little thinner too? So yeah, just looking at these, you can see that very few samples get cast out the side, and a lot of samples get cast toward the top. So that would be an interesting way to run that. And if we run this over time, I'm going to stop doing the stable sampling thing. And that way I'll have an actual series here that can evolve over time, and we'll get rid of the entropy counter eventually. So let's go ahead and take our samples here and let them roam. I thought we had a seed function, random seed. All right. Oops. And let's go ahead and run that, see what happens. And that looks pretty reasonable, right? So now the question is, can I make this a little bit more concise? Because I kind of just did that a little bit sloppy there. Because if you look at it, what we're doing is we've got more than one sort of normalization step in there than actually probably needs to happen. Hard to say. But if we SIMDI'd this, which we should do, so let's suppose we wanted, well, let's first do our random series. Let's first make our random series be a little bit more interesting, right? Let's first say that our random series is going to actually take all of the is going to take all of the lanes into account. So our random series will just by default be SIMD'd, right? So it'll have a state. When you seed it, you'll seed it with three things. And if you want, you can just avoid doing that. It'll just seed it with some garbage, right? And we could actually try to make those actually be random by grabbing them from somewhere or not. It doesn't really matter. But point being, we're going to make one of these. And what we're going to do here is say that the state value is going to be equal to a set of these. Now, I think we need to make one more of these. I think we have only one that loads just by default, but that's fine. So then, these we can implement directly in SIMD. So can we do this? So that will just work if we just change this to a 4x and implement those functions, right? And that'd be that. The rest of this stuff can all just be implemented in terms of using a slice of that value. So what we can actually do is have it so that we have random next 4x. So we can actually do this to get an entire 4-lane random result back, right? And then when we return it, code like this that only wants a U32 can just call random next U32 for x and just take one slice out of it. Right, so it can just pull one out. And then really all we need to do is make sure that our SIMD code here has that stuff in it that is the extra that we would need for this. So for example, in this case, we need each of these. And then like in this case here, where we're taking 4 of them, off we go. And then we just need these shifts, because we never implemented any shifts or anything, right? So in here, we want an XOR. Yeah. Right? And we want the XOR to be implemented probably like here. Again, really simple. And same here. So to perform these shifts, these are shifts by immediates, right? So they're going to take a value here, or I guess, I don't know what this immediate should be, but it's probably an S32 is my guess, from vague recollection. And so these are shifts. The question is, which kind of shifts are they? And in this case, I'm going to have it so that you have to do special work to get a signed shift, because signed shifts are pretty rare. They're usually meant for emulating mathematical instructions. We talked about this before, but remember, a signed shift, or arithmetic shift as it's called, happens if you're shifting to the left, then it never matters. Shifting to the left always shifts in zeros. So you get zeros, you know, all the bits move towards higher bits and the low bit comes in as 0. But if you're shifting the other way, then typically if you do what's called a logical shift, it just does the exact same thing. Zeros come in at the top and everything goes towards the lower. So it's the exact reverse of the left shift. But if you right shift arithmetic, it shifts in the same bit that was in the top. So if there was a 1 in the top bit, it'll keep shifting in 1s instead of ever putting a 0 in there. It's called an arithmetic shift because it simulates a divide of a negative number, right? Because if you imagine 2's complement, the high bit is set for any negative number, and when you do that divide by, like, you know, if I want to divide by 4, so I shift by 2, right? I want to maintain the negativeness of the number. Now, it's not perfect because you shift towards you shift towards -1 instead of shifting towards 0, right? Like, you can never, if you divided the number 1 by the number 2, you would expect 0, but you will actually get, I'm sorry, if you divide the number 1 by the -2 using this technique, you'll get 0. If you divide -1 by 2 using this technique, you will get -1 because they'll keep shifting in 1s, right? So, you know, it's all water under the bridge. Normally you don't do these kinds of things anymore. Oddly enough, we use them on Bink too, because it was faster to use lane shifts with 16-bit values to do a bunch of the color things that we were doing, but that's You know, hopefully someday those days will be over. Anyway, so what we need to do is we need to do shifts here, and we need to make sure we're doing the right kinds of shifts. So for shifts that are going this direction, right, those are shift rights. These are, and I don't remember if it's SHL or, yeah, but there's shifting right arithmetic and shifting right logical. We want logical, right? And I don't remember what these are called. So we're going to have to go look them up. There we go. And so you can see them here. So it's, yeah, these are the values. It looks like we have to cast to an M128i, which is really annoying. I don't know why they make you do that, because we don't actually want to do that, but we have to, right? So we really just want to shift the values. We don't want to treat them as PS values or anything like that. So we really just want to be able to say MMSLL PS, right? And MSSRL PS. We want the immediate versions of these because we don't need to pass the value in a register, so they're actually that. But if we try to compile that, we probably won't be able to, right? Because there's no versions of that. So what we have to end up doing is this really annoying nonsense where we do cast operations to convert these things. So we have to end up doing these cast operations in and out, right? So first we need to do a cast PS SI128 just to tell it that it's the other kind, right? So this actually goes on the inside here. Then we can shift it, and then we immediately have to cast it back. Like so. It's really dumb, and there's no reason for it. It's just awful, and it's just, I don't know why they did that. I really just don't. It's just silly and makes no sense at all. Oh, and these have to be the whole reason we did that is because there is no PS version, right? So off we go. What did you expect constant expression for this? Oh, So this is a constant, but unfortunately the compiler doesn't know that it's a constant because it's too dumb, right? So we kind of have to make this be something that can expand this to be a constant, right? So this right here is a constant. And so if, you had a language that was worth anything at all, it would immediately be able to see that this is the case because you could have written this in a way that just said, this is a constant, and then it would require this to be a constant whenever it saw it. Of course, you can't do that because it's a C++ where nothing ever works, right? And so we have to work around that somehow. So probably we won't be able to make this work exactly this way because we want to call the immediate version. We don't want to call the one where we have to stuff it in a register because it will just be slower. So in order to do this, we probably need to make these be actual functions that we can do a pound define on, right? So something like shift, something like this, that will then expand to the proper thing. So here's the left shift. Here's the right shift. And you're not really ever going to be able to do those, unfortunately. So here's our shift left. And then those will actually be able to work. Now, I did change the name of this like so. What did I not parenthesize here? So, cast PS, open, 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 close, close, close. That. And then, right, so this also has to be wrapped in an F32 to make it be able to flow through the equations properly. So we also need an F32 4x that works like this. But that's pretty easy. Right. So at that point, we should have the same random number generator working, hopefully, although it looks like we got some issue here, that will then produce 4 random numbers at a time, right? So as soon as we debug that, that should be good to go. And yeah, it will just take only one of those. So when it pulls out random next uint32, each time it will just take one of them, but then we can call this directly to get 4 of them at once from now on, right? All right, so let's double check that there. Where is our or equals? XOR equals looks reasonable. Our XOR looks good to me. Our shift, so shift right has to cast this, then do the shift logical, then do the cast back, and then stuff it into an F32. So that looks pretty reasonable to me. Let's take a closer look. So let's just take a look at what's going to happen in here. I don't really want to be threaded right now, but unfortunately I am. Let's do it this way because we'll hit one of these non-threaded first. There we go. So hopefully now we can just look at what these values are, right? Directly. So here's what we've got stuck in the values at the moment. And now we can look at how we're going to update them, right? So here's us doing our shift left XOR. Here's our next XOR. So this one didn't seem to do anything, which is a bit odd. It's like this value didn't get touched. Am I wrong about that? So here's the values. Yeah, so I'm gonna have to step into that and see what's up. So we pull out the value, we step into Who's calling us here? So we do our shift left here. Then we're going to load in that value. Did I mess up the load? I may have. I mean, we should be hitting here, and we should be having our shift. I'm not really sure, because that seems pretty weird to me. I mean, here's the values that are coming in. It's like only one of them is set, and I don't understand how that's possible. Because the values that we started with (13 bits in), they've all got, well, this one doesn't, but the rest of these all have, and plus that's a shift left, not a shift right. So all of them should have had values in there after the shift, right? So something's up with that, and I do not know what it is. Did I mess up the cast somehow? I'm gonna just go ahead and grab this out here. So if we look at the random code directly and I just let it call this specifically, so I want to see what happens if I, don't do that, and instead do something like, okay, mm128i temp equals cast. This is 13. mm128i shift. So there's the shift. M128 back, and then at the very end, so all I did there is unwrap the macro, right? I didn't do anything else to it. So it's the exact same code, as far as I know. So let's just go ahead and step in and see what that does. So we've got, to start with, here's the values that we believe ourselves to have. And I guess I can make this more explicit by actually looking at each and every one of them. So if we look at that is what we started with. Then after we do our cast, we should have exactly the same stuff, and we do. So now after we do our shift by 13, that's not a lane-based shift. Yep. Okay. Let's get the owl out. Where's the owl? That's just the whole register, which is not what I wanted. We'll just put that on there. Sorry, I was rushing through that. So if you look, I've got to balance this on my head here. We wanted the 32 version. That's the one that shifts each lane. I called the 128 version, and that shifts the entire register. Now, to be honest, I still don't think I should have seen exactly what I was seeing. But before we try to debug that any further, I should at least switch it to the correct function. Oops. Right, this is the lane count I want. I want to shift 32-bit numbers, right? So I want, well, I don't want that one, but I want this one here, right? So let's try that one more time, shall we? There we go. Now we're going to do our shift. Looks reasonable, unlike before. And now here's our back version. Oops. That's good. Here's our result. And it gets updated. Ah! So, I think we should now be okay. There we go. Although our lighting has a weird bug to it now that I do not know how we could have introduced by modifying the random number generator. So we will have to investigate that. Because that looks like a pretty reasonable sampling of the sphere to me. If we just take a look at it here, right? So, you know, I'd be pretty happy with that. Technically, what we should be doing here is we should probably be calling this in the you know, sort of multilateral way. A couple things about this that I really don't understand at the moment. The lighting seems to have gone kind of wonky, and yet it eliminated all of the flicker out of the lighting. I'm guessing that's because it's not advancing the random number generator somehow anymore. I must have done something odd there. So let's quickly look at what happened there, because I have no idea what's going on there. So the series here is used with the entropy counter. The entropy counter is getting updated. I'm not affecting that here because we're just using the series value. I literally have no idea how changing the random number generator there really made any difference, right? Oh, you know what it probably is? We're probably picking the wrong slice. So we're probably picking the slice backwards. I think I know what it is. So probably what's happening is the seed value. Yeah. So probably what's happening here is the seed value is going backwards on these. So basically, like, when you pass in only the first value for the seed, it's going into not the same slot that we're pulling from. I would expect that to be E0, but I bet it's not. That's why I usually use that R, the set RPS here. And so I think if we did that, for example, we would get our flicker back and our sampling back, right? Yeah. So that was just using the exact same hemisphere pattern every frame, which is why we ended up in that situation. So that makes sense. So strictly out of curiosity, I'm going to take a look at where we use... gosh, I wish I had a case-sensitive search here in 4Coder. I need to probably put one of those in. I think there is one. I just don't have it bound to anything, which makes it a bit tough. But let me see. Where we actually call that. So in here, is that the only place? I think that is the only place. So when we do a V3 4x and we pass those in, I think we're doing them out of order there. So I think we really want these to be... I think we're actually swizzling our lanes here, because we want E0 and to line up always. So I think these always need to be set RPS. Because I think E0 here is actually E3, like the way that the Intel ordering goes. So I think we need our MM sets to always be set Rs. I think that's actually what we want. Because that was kind of a bug before, because we were assuming that it would go 0, 1, 2, 3, but it was actually going 3, 2, 1, 0 was the way that the macro was going, right? So these... like here, for example, well, no, that looks right, though. All right. Now I'm pretty confused. So, I mean, look at what this says, right? Set packed single precision U32 floating point elements in dest with the supplied values. Here they are, right? Oh, they've got them reversed up here. Oh, that's devious. That's really devious. Yeah. So this is the one I actually wanted, right? Oh man, they double reverse it. Yeah. All right. Yeah, that's super ugly. So yeah, set R is what we wanted because we want E0 to go into the low. That's what we were assuming. So that's correct now. So I think that's all good. I'm happy with that. And also, you know, we can now, where we were previously doing a bunch of different ones here for the random numbers, right? Let me. So like in here, right, where we're creating bases off of these random bilateral 4x's right here, that could be done much more efficiently, right? So random bilateral 4x that returns an F32 x, this can just be can do this equation directly now, right? So this can just be 2 times this can just be that, right? And random unilateral instead. That can just be one of these that we just have to have the ability to do the cast on, right? So here we have to have a U32 to F32 function on that to convert U32s to F32s. But other than that, it would just work. Right? So in theory, right, if we just write one of these functions, then we're done, and we can actually just no longer have to call 4 random number iterations to fill a vector. We can just get one altogether. So if you take a look at what has to happen for this, again, also very straightforward. We know we've got one of these, that has U32s in it right now. So it's effectively one of these, right? That's backwards. I believe we want that. So we want to tell it, hey, we actually have, it's actually one of these 128i's, right? And then what we want to do is we want to do a convert, right? One of these. So it will take 32-bit integers that we have and turn them into 32-bit floating point numbers, right? Now, the rub here is that I don't think we can actually convert unsigned. I don't think there's an EPU. So if you look at how this is written, this is extended, I think this is, I think it stands for extended precision integer. Maybe? No. Precision, what is the EP? You know what? Don't quote. I have no idea what that is. The I, though, is for integer, 32-bit, right? EP. Packed. Right. That's packed. Element packed? I don't know. Your guess is as good as mine with the E is packed integer 32 versus packed unsigned would be a U here. So sometimes they do have that, right? But few and far between. So in this case, we can only do a conversion from to signed. So because that's the case, we have to take that into account in our unilateral routine, right? That's just what we're going to have to do, I think. So here in U32 to F32, where we do our cast, What we're going to have to do here is say, look, we know that this convert isn't going to convert the full range. Oops, let's go back here. Can I go back here? No, I can't. So when I do convert EPI, 32 PS, oops, I want to delete that. I still want that. So when I do this conversion, right, this will cast it first so that it knows it's U32. This is just purely, all I really want to call is this, but this is just semantic nonsense that the Intel intrinsics force you to do because they decided to have two types instead of one type. So once you're done with that, then we'll actually have the values in here, but they are signed now because some of them would have been negative and some of them would have been positive looking, depending on whether the high bit was set, right? So when we go to produce our random unilateral, after we do this, the divisor is actually not that. It's actually this, right? Because, and it's actually not a unilateral, it's actually a bilateral. So in a sense, this doesn't have to happen. This is actually the code for bilateral already. And furthermore, we could make that be true here as well, right? So this is actually the code for bilateral already, and for unilateral, we actually have to do more work. So when we actually get this in here, we would need to knock out the actual value here. We would have to knock out the sign bit, or we can just add and multiply here. But it'd be easier to just knock out the sign bit, right? Probably, I mean, I'm guessing anyway, that that'd be the easiest way to go. So we can just say, all right, let's knock out the sign bit and go from there. So to do that, we would just say, oops, we would just say like U32 to F32 and was it U32 fork? There we go. We really just want not. So we want like the inverse of that sign bit, so we can and that in there and knock out whatever the high bit was going to be on that series. Right. So we get back the value, we knock it out, and then we finish the divide there. Is S32 Max not in our platform library? It is not. So S32 Max is... I mean, I don't know how else to write it other than this way. Right? Actually, for that matter, now that I think about it, that's just the thing we actually wanted, right? If we AND it with S32 Max, which is all bits set besides the high bit, that gets rid of the high bit, and then we do the divide and we're done, right? One thing that's a little nasty about it is that if the number here in the in this case, when we do the conversion, you know what I'm saying? This isn't quite correct. The reason is because the range is a little bit different. If you look at the maximum S32 positive value, it's going to be OX7 FFFFF, right? It's going to be, well, we can do this. It's easier to talk about this with smaller numbers. So let's say we have an 8-bit number. The maximum 8-bit number signed is 127. but the maximum negative number is negative 128, right? And that's because 0 in integer is a positive number, so it takes up one, because it doesn't have the high bit set, so that takes up one slot. Whereas the negative numbers don't represent 0. There is no negative 0 in integer space. There is in floating point space. You can have negative and positive 0. That's why it's symmetric. And doesn't have a higher range for negative numbers than positive numbers. But the same is not true for integers. And so this isn't quite exactly true. For random unilateral, this will come out exactly right, because we'll convert at maximum S32, and then we will divide by that number, and we will get at most exactly 1. But in this case here, we could come up with a situation where we actually have a number slightly higher than this, and then we don't divide quite by it, right? So yeah, it's more like that, but then you lose a little bit on the other side. So it makes me think that maybe there's probably a more clever way to do it, but it makes me think that maybe we still just want to do this the same way, just to ensure fairness, because the extra op isn't going to kill us here, and that way we don't have that slight fractional bias that, you know, it would be nice if we didn't have, right? Okay. So I think that gives us a way to generate our random number ranges as well. I don't know, we may have made some mistakes there. We played it a little fast and loose, but I believe that's correct. So now we are also a little bit more efficient just when we're generating those numbers, which is kind of nice as well. And that's a good place, I think, to stop for today. So we've replaced the random number generator. We also now have the ability to actually see if our lighting converges to something reasonable, which is nice. So I think we can then improve that hemisphere sampling, like I said, next time by switching to this one, which I think will give us, and then not multiplying by the angular fall off, which I think will give us a better result. So we'll do that next time. All right, quick Q&A before I go. Is there a drawback to implement your F324X type as a union between Okay, I know what you're saying. So I really don't know if you're allowed to do that. I don't know if that confuses the compiler or not. I really couldn't tell you. I feel like there used to be, in the back of my head, I'm thinking that there was a reason you couldn't do that. Like the compiler needed to see the cast or something. But I'm sorry, I just can't remember. For some reason, I think it's slightly more complicated than that, but I just can't remember. You could try it and see. There is not Windows functions for random number generation. Well, there are Windows functions for random number generation, but you're certainly not going to call them for a real-time application, right? We want our random number generation to be like, 7 instructions long or something. And the Windows instruction, calling the random number generator in Windows is, it's a crypto random number generator. It takes, milliseconds to complete, if I remember correctly. So that's what I would say. VCAR2, you can still try my idea. Keep one subray fixed, make 3 random. Yeah, we could do that. I don't want to go to a fixed sampling scheme till I'm done looking at the sampling, though, because that's kind of the last resort. What does bilateral versus unilateral mean? Bilateral means -1 to 1. Unilateral means 0 to 1. 2 directions versus 1 direction. Vasterfout, doesn't relying on biased sampling instead of angular falloff mean that you could oversample if you use bilateral sampling? It should not. So, you know, I didn't quite do it 100% carefully there, but no. So the idea is, so let's say I'm going to place samples with a distribution that's completely uniform, right? So if I take, right, cosine theta times a uniform distribution, right? Then I am expecting the contribution of things at, I'm expecting the contribution of everything to be proportional to cosine theta, because I know that there was no weighting here, right? So this weighting was 1, and this weighting was cosine theta. So the weight of every individual area is always going to be 1 times cosine theta, right? Which is just cosine theta, which is what I wanted. If I instead change it so that the weighting of each sample is 1, but the distribution is cosine theta, that is cosine theta times 1, which is also cosine theta. So in both cases, as long as you can guarantee that your weights are set to something that when multiplied by your distribution equals the thing that you want, you're done. Right? So similarly, if, and I'm just making this up, I have no idea what this even looked like, if I made a distribution that was proportional to cosine theta over 2, then I could equivalently make something here be equal to 2, right? I could just weight each sample by 2, and then I would still get cosine theta, 2 cosine theta over 2, which is cosine theta. So you just have to make sure that your weights multiply your distribution in such a way that results in the actual thing you wanted, whatever that is. Disused. Would it be reasonable to seed your pseudo-random number generator with a random number generator provided by the OS? It would certainly be reasonable to do. It is not necessary for lighting, because lighting, it doesn't matter what the startup is. You can start up at the same value every time. The only time we would care about seeding a pseudo-random number generator by seeding it with a Windows, with something from a cryptographic source or something that was a really high quality entropy source that couldn't be guessed, is for like the world generator. Like the world generator might want to do that, right? So that you can't guess what it's going to use. Yeah, it should be possible to basically use Visual Studio 2017 instead of 2013. There may be some slight error differences, like things it complains about that it won't complain about for me, but they should be pretty clear, and they should have already been covered. I think the forums at handmade.network, hero.handmade.network, I think probably has a thread on Visual Studio 2017 as well. Or 2018 or anything else. So you should be able to to basically do it. There may be a few little hitches, but they shouldn't be hard to resolve. Engineer, can your current implementation of lighting turn a surface into a mirror? No. So there's two different kinds of light solutions that we're talking about here. One is the rendering lighting solution, and the other is basically like a global illumination term approximation, okay? And we're doing the latter, not the former. So it's very important to understand the difference between these two things because they're basically unrelated in sort of the real-time context. These aren't really typically thought about much in offline rendering because it doesn't use a single solution for everything oftentimes there nowadays, but for real time they're very different. So the thing to understand is whether or not the I vector is used. And that's the important part to distinguish these two things. So let me explain that. So let's say I have a surface and I want to ask some questions about the lighting at this surface, right? One question I could ask about the surface here is how much light is inbound on this surface, right? And let's say on average. Now that question does not take into account the I vector. It does not take into account where the viewer is. The viewer could be anywhere, and the answer to this question is the same, right? If I want to know the average amount of light coming in to this surface from all directions, that's a question that I can ask irrespective of where you're looking at it from. So that is the kind of solution that we were doing for this lighting, and we're doing that specifically because it's a very hard thing to do in real time. So you need a special system in place to get an approximation for it because asking the amount of light coming from a surface from all of these bounces is very hard to do, right? Now another question I might ask is, if I was looking at this surface from a specific direction and I hit this point, what do I see coming back at me for the light? This is an incredibly hard question. It's almost impossible to answer in real time. In fact, it is impossible to answer in real time. But certain versions of it can be asked in real time. And one of them would be, for example, given an approximate answer to this question, estimate how much of that light bounces back towards the viewer, right? So that's what we're actually trying to do. Now, in order to simulate a mirror, oddly enough, we could do that one in real time with ray tracing. That's actually easy. Why? Because a mirror is one of the only surfaces on Earth that we ever see that bounces a nearly coherent ray for every I ray. So basically, every time we look at it from a direction, it's basically just a little tiny, the cone that it needs to look at is super thin. That's what makes it a mirror. The better the mirror, the smaller the bounce radius is that we have to consider. So mirrors, oddly enough, can be done by a ray tracer in real time. They're actually trivial. The hard part is all the surfaces that aren't mirrors, which are most surfaces, right? Mirrors are really rare, but they're trivial. All other surfaces are very hard. Why? Because most other surfaces gather light from everywhere for every I ray. So if we look at it from this direction, typically we gather light from all incoming directions, which requires huge numbers of rays to sample, instead of a mirror which just has just one direction we sample. So if all surfaces were mirrors, what a wonderful world that would be. Of course, not really, because then we'd bounce around forever, but that's a different story, right? So if all surfaces were mirrors or lights, right? So either they had a single uniform brightness value they were shining at you, or it was a mirror, hey, rendering would be trivial. We'd be done, right? We could have perfect simulation of the real world. It would just be done. No problem, right? Sadly, it's not. So what are you going to do? So as a result, mirrors are actually quite easy. We're not going to do them in Handmade Hero because it would require a whole separate scheme at render time to do a ray trace when we detected those materials to do a ray trace. We're not going to do that because it's just not worth it, right? But if you cared about that a lot for your game, it's actually not that bad to put mirrors in. The hard part is everything else. The hard part is a cave with a light at one end that kind of has a curve and you see light around the corner. That's the hard part of lighting in most situations. And it's really hard to get right. Long Balloon, you mentioned a few times that later on during world generation we will do a better job of adding sample points. Are these sample points limited to static terrain, or do you have ideas about how to handle terrain that can be in motion or altered in some other way? Yeah, I mean, we have two options. First of all, the sample points are stuck on the surfaces, but they will move with the surfaces. So they're not, it's not restricted to static terrain, but the distribution of points and how they relate to each other may very well be kind of static E. So we might have to do things like, if we want the lighting to be always good, when we move terrain around, we may have to try and update sample points constructively as part of that. And I don't know how we'll, if, you know, maybe we will try to do that or maybe we won't. What I meant with the question is that if a surface B is nearly above surface A but perpendicular to it, is there a risk a lot of rays originating from A could hit B and thus contribute a lot even though the angular falloff will prevent that? That's not the angular falloff we're talking about. So the angle of the two surfaces to each other is not part of it, right? We're just talking about the angle to the normal. And no, it does not matter what kind of surfaces you're talking about. The sampling rule I wrote is just true, as far as I know, anyway. Right? So in the case that you're talking about, so you're talking about something like this, right? Angular falloff is only talking about the sampling. This part is not included. So the fact that this angle happens to be steep to that angle, that's not actually the angular falloff we're talking about. And I don't think that term is in there because, is it? It might be. But if it was, that term would stay in there, right? It's only the term for this that we're talking about, the normal dot the ray direction. I'm talking about bilateral sampling. You mean bidirectional sampling? We don't do bidirectional sampling. If we implemented bidirectional sampling, then we would have to figure out how we want to do that, because that's has a bunch of implications that are different. So I don't know, that's a whole different, we don't even really know how we would change our routines exactly for that. So moving to bidirectional sampling would be a whole different thing. Not 100% true in terms of the diagram. What diagram are we? I'm not sure what diagram we're talking about. N30 shadow. Or Neo shadow, I guess is probably how to read that. The geometric concept of rays breaks down for caves or any cone. I don't know what you're talking about. The reflection diagram breaks down for the cave example. No, it doesn't. Why does the reflection diagram break down for the cave example? I mean, it's, you know, I'm just talking about this, right? And so if you have something emitting light here, and you're talking about trying to figure out what the light is here, since you can't directly see the light source, I was talking about things where you have to account for the fact that, you know, the lighting from this is maybe bouncing in this fashion, right? So what you're effectively trying to do is build a system that can approximate get approximate solutions that still produce the fact that there should be some lighting here, even though the only way to get lighting there is through indirect bounces, right? You know, there's one type, there's another type, and so on. But what reflection, I don't know what you mean by the reflection diagram breaks down that case. It's the same reflection equation regardless of what this geometry looks like, right? I was going to wait a second to see if there was a reply to that before. I think otherwise we're done with questions. The illumination problem. So are you just more talking about if you actually wanted to figure out the solution to a well, I guess I don't know what you're actually talking about. We're not talking about trying to measure photons here, right? Like actual what happens with photons when they bounce around. I mean, technically you're into quantum mechanics there at that point, right? We're just talking about if you actually want to take and figure out a reasonable solution to sampling the light coming in the hemisphere instantaneously at a particular point, then you can sample however you're going to sample. You can sample proportional to a weight and then not weight, or you can weight and sample uniformly. And that is just true, period, right? Now, what you're talking about is something completely unrelated to what we're talking about. You're talking about whether or not you're talking about how the physics of lighting are going to work in a particular case, right? As to whether ray casting can actually capture what's going to go on or something like that. But that's not relevant to sampling, right? Sampling, that thing is true about sampling, period. It's not like it's an approximation. It's just true, right? And so you might end up in a situation where the thing that you're sampling, you've used an approximation to, is as in the case where if you think that light transport along rays is not sufficient to capture what you actually wanted to have happen, then you would be in that situation. But that's a separate topic. If you don't think rays are accurate enough to capture the light transfer, then you have to deal with that. But the sampling part is just true. It does not have, nothing on number file can really change that fact. That's just how sampling works. Because it's just a property of summations. you can sum up n things weighted by wi that are uniform, or you can sum up a thing distributed by wi weighted uniformly, and you will get the same answer. That's just math, right? It doesn't really have any dependence on the thing in question, if that makes sense. So hopefully that answers that question. And suffice to say, the number of approximations we have to make anyway to get things to run in real time means things like whether we would care about the approximation of ray transport is way beyond anything we would care about, because we've already had to make, already the fact that we're not going to really take into account the textures of surfaces at all, is a pretty huge one, because these surfaces in the game will have textures mapped onto them, and we're not going to sample those textures, right? We're not going to take the extra time, probably on a bounce, to sample the textures, so the sample points will just have fixed color, and that'll be what they are, right? So, in that sense, it's important to keep in mind that if you're even thinking about the degree to which rays might not capture some lighting thing, you're not in a realistic space, because you're already past, you've already made enough approximations by that point that it would not be something you should really be considering, if that makes sense. But I do want to underscore the point that no, the sampling part is true. It has nothing to do with your representation of light. It doesn't matter. Your representation of light could be completely different, right? And it would still be true. So the sampling, it's really important to understand, the sampling is not an approximation. That sampling thing is true, right? And it holds true regardless of what you're doing. And if the underlying thing happened to have some kind of a inaccuracy to it, then the underlying thing may be at fault, but the sampling part is not. It's mathematically correct, if that makes sense. All right, so I think we are good to go here. Oops. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always go to handmadehero.org, and if you pre-order the game, it comes with a source code, so you can follow along at home. We will be back next weekend, and I just want to go ahead and play with that hemispherical sampling and maybe take out the angular weighting term and just bias the samples to be proportional to cosine theta anyway. That's what I think I'm going to go ahead and try, and we'll see how that goes. There may be issues with that due to the fact that how much we're sampling may not be sufficient, but we'll see what we can do. That's it for this week. Until next week, have fun programming, everyone, and I'll see everybody on the internet. Take it easy, everyone.